All right, here we go. So this is video 2.3. We're going to talk a little bit more about non-constant acceleration today, and specifically we're going to focus on how to use the integral. If you watched video 2.2 and a half, which was about sort of how to take an integral, there was a lot going on in that video. And I'm hoping this video will help kind of tie the pieces together, and hopefully, whatever, help clarify things. There are a lot of F's in that video that made it a little bit confusing, all right? And I'm thinking this might be a little bit more intuitive, all right? And then the other thing is I'm going to try to start each of my videos from now on by making a list of sort of the things that you should get out of that video. This list here is actually a little bigger than usual because I included some of the things that you should have gotten from previous videos, all right? Really quick, remember, anytime you're trying to find average velocity, it's displacement over time. You can only use VF plus VI over 2 if the acceleration is constant, so watch out for that. All right. Anytime you're trying to find average acceleration, you have to do change in velocity over time, okay? So those are definitions. I really need to lean in that direction, okay? There will definitely be problems where you need to find average velocity and average acceleration, and unless the acceleration is constant, you got to go to those two. All right. So this right here is basically, what would it have been? Video 2.2, I guess. Okay, this is all the stuff on derivatives. Oh, that green is really dark, isn't it? Changed my ink colors. Okay. So just remember, the derivative of position is velocity. Cool. We also learned that the derivative of velocity is acceleration, okay? These two ideas here are actually going to be instrumental in today's video, okay? Because we're going to learn how to kind of go the other way. All right? And then down here at the bottom, we start to get a little bit into the integrals, okay? So, in the same way that the derivative of position is velocity, it turns out the integral of velocity is position. The integral of velocity is position. All right? So remember, in video 2.2 and a half, I talked about the difference between definite and indefinite integrals. Okay? Remember, a definite integral gives change in a value, whereas an indefinite integral gives the actual value. Okay? And the reason this all works is because the derivative of position with respect to time is velocity, right? And so when you do your integrals, the integral of velocity is either position or change in position, depending on whether it's definite or not. So, okay? All right, so, and then similarly, since the derivative of velocity with respect to time is acceleration, that means if we integrate acceleration, we're either going to get velocity or change in velocity, okay? The change in velocity will come from a definite integral, so time 1 to time 2, okay? So, and then the last thing I will remind you of is that anytime you do a definite integral, these definite integrals that I've got here and here represent the area under the curve, okay? So the area under a velocity time curve is the same as the definite integral, okay? So, yes, all right? And similarly, the area under an acceleration time graph is the same as the definite integral, the change in velocity, all right? So anyway, this is all sort of a big overview, kind of a quick crash course. All right, I keep saying crash course this year. So let's jump into this and do some examples, all right? Okay, so suppose I give you this. Suppose I tell you that an object has a velocity time graph that looks like this, okay? So first of all, really, here, the first thing you should be thinking is you should be looking at this graph and you should be going, oh, well, my velocity is 5 meters a second. It's constant. That means my acceleration is 0. Acceleration is also constant, right? Okay, and so really we shouldn't even be using calculus, all right? If you get one thing, well, no. You gotta get a lot of things out of this video. But absolutely, I want to reiterate, anytime your acceleration is constant, really you should not be using calculus, all right? You should be using the 2.1 equations, the kinematics equations, all right? But just because I'm trying to help you guys understand calculus a little bit better, I'm going to do some of this stuff with calculus, all right? Okay, so suppose we wanted to know the object's position at, a time, like whatever, 6 seconds, all right? Well, think about what the position time graph is going to look like. Since my velocity is 5 meters a second, that means that the slope of the position time graph is 5, right? Specifically 5 meters a second. So what does the position time graph look like? Well, position, time, position, right? Okay, so what I know is that the slope of this position time graph has to be 5. So let's draw a line. Here we go. Slope of 5, right? The problem is there's an infinite number of lines that have a slope of 5. So it could be this, or 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 it could be this, right? Those all have a slope of 5. Okay, so I really can't find the position at a given instant, all right? But I can certainly find the displacement between two instants, right? Okay, so using kinematics equations, that would just be the same as saying, oh, well, displacement is velocity times time, right? Since my velocity is constant, all right? Sometimes it'll be written this way, velocity times change in time, right? How much your time changes. Okay, but so just to make a point, let's do this using some calculus, which again is silly, but I want to make sure you guys kind of see what's going on here, rather. All right, so here we go. So look, so we know that velocity as a function of time is the derivative of position with respect to time, right? Okay, so what that means is that if I take, well, so let's pick two instants. What two instants? Let's do between t equals 2 and t equals 7. How about seconds? I guess I should put units on stuff. All right, so I'm looking for the displacement between two things. So because I'm looking specifically for a change between two fixed instants, that tells me that I need to take a definite integral. All right, so here's what that definite integral is going to look like. I'm going to say, so because of this, what that means is position as a function of time is the same as the integral of velocity with respect to time dt, right? Okay. Okay, so these two statements here are basically the same thing, all right? But I'm not looking for the position, I'm looking for the change in position, and so I need to put in my bounds, all right? Now, because this is dt, that tells me that my bounds that go here and here should be times. So I want the change in position as my time runs from 2 to 7 seconds. Okay, this is a 7 up here. Ooh, 7 up. The Uncola. All right, that's a 7 up there. Okay, so let's solve this thing here. All right, so that means then that our displacement as a function of time is the integral from 2 to 7 of v of t. And velocity is 5, right? So 5 dt. So now you ask yourself, all right, well, what's the integral of 5? And so then the question is, what function would I have to take the derivative of to get 5? Well, 5 is 5 times t to the 0, right? And so that means before we took the derivative, our exponent must have been 1. Right? So this looks like it's 5t, right? So that's the derivative of 5. And then I want to evaluate it at 2 and 7, right? Okay, so notice I changed my notation here. I got rid of my integral symbol and put in this symbol that means evaluate it at these two values. Okay, so now I'm going to do 5 times 7 minus 5 times 2. Okay, 5 times 7 minus 5 times 2. Okay, and so that gives us 35 minus 10, which is 25 meters. Okay, and so there's our answer. So graphically, what did we just find there? So notice what we just did is we did 35 minus 10. All right, remember, an integral is the same as the area under a curve. So what we just did is we found the displacement between, oops, I need to scroll up a little bit more. We just found the displacement between 7, oh, I don't like that blue. We just found the displacement between 7 and 2, right? So technically speaking, the displacement is the area under the curve. The displacement is the area under the curve. So the displacement should be this area here, okay? Because what did we do? Well, we went at 5 meters a second for 5 seconds, right? So let's think about what the 35 and the 10 are, right? Because down here we did 35 minus 10. So what is the 35 and the 10? Well, the 35 is how far we went in the first, how far we would have gone in 7 seconds. So here's what the 35 is. 7 times 5, right? So it's the area under this triangle. That's the 35. Okay? And then minus 10. So then we subtract it out this area. Okay? So if you take that red rectangle and then subtract out the blue rectangle, it gives you the yellow one. All right? So that's the deal there. All right? So, calculus. All right? So let's do one more example like this where the velocity is constant. Well, better yet, let's further analyze this example where the velocity is constant. So in this example, to be clear, we did an indefinite integral, right? No, we didn't. We didn't. To be even clearer, we did a definite integral, right? Now I'm worried I misspoke before. Everything that I've done here has been a definite integral. If I said otherwise before, I misspoke. I hope that I did not. All right, this is all definite integral because we know our bounds. Okay, so let's do one now with an indefinite integral, okay? So, same exact graph, same exact velocity, all right? So remember, the problem was we couldn't find our position before because there are all these different possible graphs, right? We didn't know which, we knew what our slope was, but we didn't know what our y-intercept was. It could have been anything, right? Okay, so the only time you're really going to use a definite integral is if you know some point on your integral curve. Okay, so let's do this. So it says, suppose I know the position at some time. I can write an expression for the position as a function of time. All right, so suppose I told you this. Suppose the problem said, suppose that the position after, I don't know, let's say 3 seconds is, how about, I don't know, about 12 meters, say, okay? Let's find an expression for the position at time t, okay? So here's what we would do. We would say, so we know that the velocity at time t is 5 meters a second, and we know that velocity at time t is the derivative of x with respect to time. So this statement here is the same as position at time t is the integral of velocity at time t with respect to t. Okay? I don't know if this helps any, if this helps you figure it out. If you multiply both sides, this is a little bit mathematically sloppy, and there might be some calculus teachers out there looking at this. If you multiply both sides by dt, that gives you the v dt, and then taking the integral turns the dx into x. Okay, I don't know if that helps any, but that's kind of how I always think of it. All right, so let me clear up some ink here. All right. So I want to integrate this mess, right? So notice this time this is an indefinite integral. So remember, when you do an indefinite integral, that's when you've got to do the stupid plus c thing, right? So our position at time t is the integral. V of t is just 5 dt. Integral of 5 is 5t plus c, right? Because look, if I take the derivative of this, the derivative of 5t gives me 5, and the derivative of c is 0. That's the problem, is that no matter what this constant is, the derivative is 0. And we don't know what that constant is, okay? So that's our, oops, I wanted that to be orange still. So that's our deal. Oh my gosh. Well, let's leave it. Okay, so it's blue. Deal with it. All right, so we got to find out what that is. So now, here's what we know. We know that our position at time t is 5t plus c, right? So now is when we use that given information, right? Remember, I told you that after 3 seconds, our position was 12. Oh, after 3 seconds, our position is 12. Our position after 3 seconds is, oh, well, that's the same as 5 times 3 plus c, and it's 12. So that's 15 plus c is 12. Subtract 15. Oh, c is negative 3. Aha! Ooh, let's get a new color. My position at time t is 5t minus 3. Kabam! All right? So, that's the deal. Those are the 2 types of integrals you'll need to do. All right? So, let's try another one here. All right? So now we've got this new graph, velocity at time t, and you can see that it's got slope here. But I also notice it's a straight line, right? Okay? So really, again, we shouldn't be using calculus here, all right? So if I asked you for, let's suppose I asked you this. Find the displacement between t equals 1 and 6 seconds. All right? Well, use kinematics, right? Look, after 1 second, my velocity initially is, what is that, -9. After 6 seconds, my velocity is 6 meters a second. The time that elapses is 5 seconds. So find your displacement. Plug in your numbers. So you get 1/2 VF is 6, VI was -9, times the time, which is 5 seconds. So what is this? -3, 1.5, so that's going to give you 7.5 meters, right? Okay. So there you go. The other way you could do it, if you wanted to be a little bit more calculus-y, is remember that displacement represents the area under the curve. Now, when we say area under the curve, here's what we're talking about. So let's do this. So here's our curve. Now, when we say under the curve, it's technically not always under the curve. It's technically the area between the curve and the horizontal axis. Okay? So, what I would be looking for is the area of all of this and this. But you got to be careful because this chunk here, which I'm now turning to green, actually has a negative area. Oh, I did my math wrong here, didn't I? Sorry, this does give you negative, right? Because this is -9 there, so that would make your answer negative. Okay, so let's take a second and do this and see if we get the same answer. All right, so let's find the area of this sort of greenish blob here. So let's see, it's a triangle. Let's see, this side is 9. Let's see, we're going from 1 to 4, so this side is 3. So 9 times 3 would be 27, but we want half of that, right? Because it's half base times height. So what's that give you? -13.5, right? Meters. And notice the units do work out when you do area, right? Because it's meters per second times seconds, base times height, right? Okay? And then over here, for this chunk, let's see, this side is 2, this side is 5. So half of base times height, this guy has an area of 5. What's going on here? 13.5 minus 5 gives you 8.5. Oh, this side's 6. Sorry about that. Which means our area is 6. So now, when you find your total area then is going to be 6 plus negative 13.5 gives you negative 7.5. Okay? So that's that. Cool. I think I'm going to leave that one at that. You really shouldn't be using any calculus to solve this. So, when do you have to use calculus? Suppose I give you a velocity time graph that looks like this, okay? So the first thing you ought to notice is, holy cow, my velocity is changing. It's clearly not changing at a constant rate, right? Because sometimes the velocity is increasing, sometimes it's decreasing, right? So, how do we deal with this? All right, well, so occasionally, well, I'm getting ahead of myself. All right, so you would have to be given the equation for the function. So here's the equation of the function, okay? And so the problem wants us here to find the displacement between 0.2 and 1.4 seconds, all right? So here's my equation for velocity as a function of time. So I should be thinking, oh, well, velocity as a function of time is the derivative of position with respect to time. Oh, well, that means that, remember, multiply both sides by t, or dt, and then take the derivative. Ah, geez, try that again. Let's rewind and say that again. I should be thinking that the velocity at time t is the derivative of position with respect to time. So, I should be thinking, multiply both sides by dt, and then integrate both sides to get this. Position as a function of time is the integral of velocity with respect to, velocity as a function of time, dt, right? Okay, but I'm not looking for position, I'm looking for change in position, right? So I'm going to put a delta x here, and then my bounds need to be according to time, and that's what I'm given, 0.2, 1.4. Okay, so my displacement is the integral between 0.2 seconds and 1.4 seconds, the integral of v of t. So that's this mess up here. So here we go. So we're going to go negative 120 t to the 4th plus 360 t cubed minus 330 t squared plus 90t with respect to time, right? Okay. So let's take our derivative. So this becomes, let's see, so I want the integral of negative 120 t to the 4th. So that means that the question is, what did I take the derivative of to get that? So this must have been t to the 5th before I took the derivative, right? All right, which means then, or when you bring this down, you're basically going to have 120 over 5, right? Oops, let me try that again. Writing is a little sloppy there. 120 over 5, right? Because that way when I multiply by 5, the 5's cancel, right? And don't forget that negative sign. Okay? Plus, when I take the derivative of this guy, let's see. Well, before I took my exponent or derivative, this must have been a 4, so it must be t to the 4th. And then it must have canceled, so 360 over 4. Okay? Minus 330 over 3 t cubed, right? Plus t squared, 90 over 2, right? So there's my integral, and then we need to evaluate between 0.2 and 1.4. Okay, notice I changed my integral to an evaluate. Okay, so let's simplify this a little bit. So once you simplify this mess, negative 120 over 5 is what? Negative 24 t to the 5th plus 90 t to the 4th minus 110 t cubed plus 45 t squared. 0.2, 1.4. Okay, so now, somewhere I have this written down. Where did I put my paper? Here we go. So, when you plug in the 1.4 into this mess, you end up getting 3.02624. No, you don't have to keep all those decimals, I'm just being weird. All right, minus, when you plug in the 0.2 into this mess, you get 1.05632. So when you subtract, you end up getting 1.96992 meters, and there is your answer. All right. Now, to be clear, what that represents is, well, so hold on, I probably scrolled too fast there. There you go. All right. So what that represents is this area. Let's see, we went from 0.2 to 1.4. So what we just found is this whole area. We found this positive area plus this positive area minus, or take away this because it's all negative, right? Okay, so that's what that is. That's what we just found. Okay. There will occasionally, I've seen a couple of these on like old FRQs where they'll give you a graph like this, but they won't give you the equation, and they'll ask you for, the displacement. They'll ask you to find the area, and you'll have to do it by approximation. So it'll basically just be counting squares. Okay. So make sure if you have to do it that way that you're cognizant of how big each square is. You know what I mean? Like here, each square happens to be one tall, but your time. Each time square is what? Let's see, 0.05 seconds. Okay, so you just got to be careful of that. All right. All right. So that was. Yeah, I talked about that. We were looking for displacement, so that was all a definite integral, right? So let's do another one that's indefinite. We're coming on time. I'm at half an hour. Totally. Well, this one's long. Deal with it. AP, welcome. All right. So here, this one's basically the same. But this time, you're trying to come up with an expression for the position as a function of time. Okay, so notice we've still got the same function that I had a minute ago. All right, so I'm going to kind of plow through this. This time, it's a definite integral. Okay. So we know that. My brain just totally stopped there. We know that velocity as a function of time is dx dt. That means position as a function of time is the integral of velocity of time with respect to time, right? So here we're looking for the position. We're looking for an expression for the position as a function of time. So you're just going to integrate, just like we did before. So integrate, integrate that mess, okay? And you get that same thing that we just had a minute ago, which was negative 24 times t to the 5th plus 90 times t to the 4th minus 110 t cubed plus 45 t squared. Okay, so, but then, because we took a definite integral this time, because we took an indefinite integral, right? Because we're actually, we don't know our bounds, right? So we got to add on this plus c. Okay? So then all you're going to do is you're going to say, oh, and I also know that the position after 1 second is 5 meters. So the position after 1 second is 5 meters. All right, so all you're going to do is you plug 1 into all of this and solve for c. So you get 5 meters equals, if you plug 1 in here, you just get negative 24 times 1 to the 5th plus 90 times 1 to the 4th minus 110 times 1 to the 3rd plus 45 plus c, and solve for c. And if you do that, the c ends up being, I think this whole mess, if I remember right, gives you 1, which means that this guy has got to be 4. Okay, so my final answer is this, but you replace your c with 4. Okay, so that is that. So everything we did here was for velocity and time. Okay, and by integrating, I could either get my position or my change in position. All right, what if I give you an acceleration time graph? All right, well, it's basically the same process. All right, the only difference is now taking an integral will give me either velocity or change in velocity, right? Because the derivative of velocity is acceleration. That means the integral of acceleration is either velocity or change in velocity. And so then the only difference is whether you take a definite integral where you know your bounds, or an indefinite integral where you don't, okay? I'm going to go out of order on the notes here. Let's actually do this one first, because on all the other examples I've done the definite first, so let's do the indefinite first this time, okay? So here we go, we've got this acceleration time graph. Clearly the acceleration is not constant, right? So we can't use kinematics, we got to use calculus, right? So here's what I'm thinking. I'm thinking, oh, acceleration as a function of time is the derivative of velocity with respect to time, right? So that means that velocity as a function of time is the integral of acceleration with respect to time, right? And so that means that velocity as a function of time is the integral of this mess, right? 3t squared minus 24t plus 30. Oh, there's not supposed to be a t here. This is a typo. Darn it. Hopefully I'll remember to fix this before I print it. This is just supposed to be 33. Okay. Typo. So, why am I dumb? Sorry. Yeah. So, what do we got? Sorry. 3t squared minus 24 plus 33. Okay. 3t squared minus 24t plus 33. And about the integral of that, right? Now notice, I don't know my bounds, but I do know a point, right? This is telling me that my initial velocity is negative 15. So the velocity at time 0 is negative 15 meters a second, right? So let's go down here. So we got to take our derivative, right? So, or take our integral, right? So the derivative of 3t squared is what? T cubed, right? Because if you take the derivative of that. Okay, so this is v of t equals t cubed. The derivative of negative 24t, I think, is 12t squared, because if you take the derivative of that, it gives you negative 24t. And then plus 33t. And then we don't know our bounds, so I got to go plus c. Cool? And then I go, oh, well, v at time 0 was, what did we say it was? Negative 15. Well, let's put in 0. So you get 0 minus 0 plus 0 plus c, right? And that equals negative 15 meters a second. Oh, that means c is negative 15 meters a second. So v at time t then is, so v at time t, man, my blue and my green are too close, aren't they? I wonder how they look on your screen. So you get t cubed minus 12t squared plus 33t minus 15. Okay, and so now the question wanted to know, what's the velocity after 3 seconds? So now I just plug in 3 and solve it. And if you do that, you get, it looks like 2 meters a second, if I did my mathematics correctly. All right? Okay. Now, some of you might be thinking, couldn't I have done this with a definite integral? And the answer is actually yes. You could have. Because what you could have done is you could have taken the definite integral between t equals 0 and t equals 3 to find the change in velocity. It turns out to be 17. All right? And then you go, well, let's see. I know my velocity started at negative 15. So then if I add 17, which is how much it changed, then it gives me that same 2 meters a second. All right? Okay, now, finally, this one I'm not going to run through it. It's basically the same idea. So now we're looking for, oh, no, I do have to run through this. Ooh, this is big. Big, 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 big. Trying really hard not to do extra examples, but I don't need to. This one is huge, okay? All right, so we're going to find the average acceleration here. So this is what I was talking about at the very beginning of the video. I'm going to jump back to this for a minute. Remember average acceleration? What did we say? I said there's only one equation to find average acceleration, right? Here it is. Look at this. Just change in velocity over time. So in order to find this average acceleration here, somewhere, we need to find, so A average is change in velocity over, technically we're changing time, but whatever. So we need to find our change in velocity between 1 and 5 seconds. So this is a definite integral. I'm going to find the change in velocity using a definite integral and then divide it by the time. All right? So I know that acceleration is the derivative of velocity with respect to time. So that means that velocity is the integral of acceleration with respect to time, but I want to change between 1 and 5. Okay, so this is my arrow and my triangle are trying to get all nakey-outy. Okay, so we want the integral between 1 second and 5 seconds of the acceleration. 3t squared minus 24t plus 33. Again, forget about the t there. All right, we're almost done here, so this gives us, we already took this integral, right? It's t cubed minus 12t squared plus 33t, and then evaluate it between 1 and 5. Plug in your 5, plug in your 1. Did I already do this? I did. So if you do this, you end up getting, when you plug in 5, you get negative 10, minus when you plug in 1, you get 22. And so subtract this and you get negative 32. That's our change in velocity, meters per second. How long did that take? So let's see, so that's our change in velocity. Oh man. That's our change in velocity, okay? And so then you go, oh, acceleration is change in velocity over time, right? So negative 32 meters a second. That took 4 seconds, right, between 1 and 5. So that's why we use delta t. It's technically 5 minus 1. So anyway, you get negative 8 meters per second squared. Okay? Let's see if that makes sense. So between a time interval of, oh shoot, what just happened there? Between a time interval of 1 and 5, does it make sense that our average acceleration would be negative 8? That makes some sense, right? Cool? Cool. I wonder. I don't know if this is true or not. Looking at this, that makes me think, I don't know if this is true or not. I'd have to sit down and math it out. But it looks like this area is equal to this area. All right? So, there you go. Happy physics. Okay.